Hello everybody and welcome to the circuits tutorial. This will be a 3 parts tutorial and hopefully each part will not exceed 20 minutes. In the very first part I'm gonna go very quickly over what logic gates are and then we're gonna go to sheet 3 and solve some circuits. So let's get to work. So right here these are the 6 basic logic gates that we have. And this one here is called NOT. It takes one input and one output, and what it does, it inverts the input, right? So if this is the input, when it's 0 it becomes 1, when it's 1 it becomes 0. This one here, very famous, is called AND. It has 2 inputs and 1 output. So usually guys, what we do is we arrange the input like this, right? 0 0 0 1 1 0 1 1, right? Because these are all the possible combinations. And then I'm going to put the output right here. So the AND gate, what it does, it only outputs 1 when all the input is 1. When this is 1 and this is 1, any other combination it puts out 0. So the output will look something like this, right? All zeros except when both inputs or all input is 1. Now this is OR. This is the OR gate, and in the OR gate again we're going to do all the combinations. In the OR gate again it takes 2 inputs and it outputs 1 input, and it outputs 1 if any of the inputs has 1, right? So the output looks like something like this, right? So the rule here, as long as you have 1 in the input, you can have 1 in the output. This is XOR. Now XOR or XOR sometimes is called the exclusive OR. Some people call it an odd detector, right? Because it outputs 1 only when there's only one in the input. To make this easier for you, this is called an odd detector. It only outputs 1 when these 2 inputs are different, right? And they're only different when one of them is 1 and the other is 0. So here it outputs 0 and here it outputs 0. Okay, let's drag this a little bit up. So this one here is called NOR. This one is called NOR, and in this one, if this is the input right here, 0 1 1 0 1 1. Now this outputs 1 only when all input or both input is 0. So it's just going to put 1 here and then everything else is 0. Now this here is equal to OR and then NOT. But again, it's easier to memorize it like this, and instead of saying, okay, this is the NOT of OR, no. Just make sure when you have a NOR gate, it only outputs 1 when both inputs are 0. Anything else, it doesn't output 1. The NAND gate, the last one, this is called NAND, right? So the NAND gate, this is the input again. So the NAND gate outputs 1 when there's 0 in the input. So as long as you have 0 in the input, the NAND will put out 1, right? So 1 here, 1 here, 1 here, and 0 here because there is no 0 in the input, right? Again, you can think of it as AND and then NOT. So 2 gates combined, but I think it's easier to think of it this way. As long as you have 0 in the input, then you're going to have 1 in the output. Okay. So that was a very quick recap over basic logic gates, and then we're going to go very quickly and solve this circuit right here. You have this circuit in the book, it's not in the sheets, but it will be a very quick example before we go into the sheet. So to solve any circuit, guys, we're going to have, it will either be one of 2 ways, right? One, we can do it manually, right? We can do it manually, okay? Or we can use Boolean expressions. So these are the two ways that we will use to solve any circuit, okay? Using Boolean expressions or Boolean algebraic expressions, or doing it manually. So when to know which one we're going to use, if the circuit has a feedback loop like this one here is called a feedback loop. If the circuit has a feedback loop, we're going to do it manually. If it doesn't, then we're going to use Boolean expressions. So this here has a feedback loop, so we are going to do it manually. So it's very useful in so many cases to try to know what the purpose of the circuit is before you solve it, if that's possible. Because when you understand the purpose of the circuit, or the relationship between the input here and the output, this is the purpose of the circuit, it will be very easier for you to solve it. And when I say solve it, I mean to come out with the truth table. So this here is a flip-flop, right? We're going to call this S, and we're going to call this R, and we're going to call this O. So the truth table will be like this: S, R, and O, right? Very good. And usually, let me draw some line here. Okay. So usually all the combinations are 0, 0, 0, 1, 1, 0, 1, 1, right? So the purpose here is to fill this out. When we know what the output is, we would have solved, that means we solved this circuit. Now for the flip-flop, again, the purpose, knowing the purpose will help you solve it. When you put, the flip-flop works like this. If you put 1 here as an input, the output is supposed to be 1. When the input returns to 0, the output should still remain 1, right? Then when you put 1 in the R, the output is supposed to flip, right? That's why we call this S and this is R, because the flip-flop is something that is called SR latch, because S means set. When you press set or put 1 here, it sets the circuit, the output, to 1. When you press reset, that's why we call this R. When you press reset or put 1 here, it is supposed to reset this to 0, okay? And when you have 0 here and 0 here, the last state of the entire circuit is preserved. Okay, so let's get to work. Now it's useful sometimes, see that we have all the configuration, but it's useful sometimes in some circuits like the flip-flop to start when one of the entries is 1. So we're going to start here. Why we are starting here? Because this is going to make our life easier, because we know that when 1, as we said, when we set this to 1, this is supposed to be 1, right? So let's try. Now I'm going to use things like this, okay? When I put 1 here, I'm going to put a very small 1 here too. Why? Because I call this the level of input, because when I insert another input like 0 here, I'm going to put number 2, and this is going to tell us that this is the second time we do it. If you are confused, just follow with me and you're not going to be confused anymore. So I'm sorry about that. So we're going to put 1 here. So this one, remember this is an OR gate, so it has 1, so it will output 1 here, correct? Okay. And remember we are doing this, so we start with 1 in the S and 0 in the R. So we're going to put 0 here, right? And this 0 here becomes 1 here, correct? So 1 and 1 in the AND gate, that goes here, and it becomes a 1. And it becomes a 1, right? So 1 and 1 in the OR, the output becomes 1. Okay? Okay. So we have done this part. So this becomes 1. All right. The second part, we're not going to do this. We're going to do this. Why? Again, because this is going to make our life easier, because since we know the purpose of this circuit, we know if we enter 0 here and 0 here, this one is supposed to continue being 1, and that's why we are doing this. So I'm going to put 0 here, because this is the second time we do this. We're going to put 2 here. So 0 and 1, right? 0 and 1. This is an OR gate, becomes 1 here, right? But this is the second time. And we're going to put another 0 here, okay? Now you know what this number means. 0 here, it's going to become 1 here, correct? So 1 and 1 in an AND gate, again, that's a 1 here. So now we have 0 in the second cycle. We could call this the cycle number. In the second cycle we have 0 and we have 1. In an OR gate, this is going to output, in the second cycle, it's going to output 1. So this is 1. And this is how it's supposed to work, right? We know that the flip-flop, when you give it 1 here, and 0 here, you're supposed to have 1 here. When you turn this into 0 and 0, the previous state is preserved, so you still have 1 here. Number 3, we're going to do this. We will now move to this one. Again, why? Because we know that when we enter 1 in the reset and 0 in the set, this is supposed to flip or be the opposite. So the outcome, we expect this to be 0. And that's why we call this a flip-flop, right? Because it flips. So let's do that. Let's put 1 here. So, sorry, 1 here. This is the third time we do this. So this one becomes 0, right? So it becomes 0 here. And we're going to put 0 in here, correct? So 0 and 1, that becomes 1 here, because this is an OR gate. If you have 0 and you have 1 from the previous cycle, that becomes 1 here. Now in this cycle, 1 here and 0 in the AND gate, this is going to give us 0, right? There you go. So 0 here. Now in this cycle, 0 and 0 in an OR gate, that gives us a 0. Now, you see why I'm using these numbers? Because it's telling me, okay, that was the first output, that was the second output, and that was the third output. So since we are in 3, this is the third output right here. So it works. That is a flip-flop. We can try 1 and 1, right? But since we know the purpose, we know that in a flip-flop you really should not put 1 and 1, right? Why? Because the purpose is you either put 1 here and 0 here to set it to 1, or you put 1 here and 0 up there to reset it to 0, or you put 0 and 0 to preserve the previous state, right? 0 and 0 preserves the previous state. But you really shouldn't put 1 and 1. If you want to try it, maybe we can. Well, so we're just going to indicate, if we are doing it, that this here is forbidden, right? Forbidden, or we are not supposed to do it, because since we know the purpose, what is the purpose of 1 and 1? And we need to denote here that this here, right, this is to preserve the previous state. Preserve the previous state, right? Okay, so let's do 1, 1 and see what the outcome would be. So we're going to start with the set. So if I put 1 here, so 1, oh, that's 4, I'm sorry. If I put 1 here, so 1 and 0 in an OR gate, this will be here a 1, right? And if I put 1 here, so this is a NOT gate, it's going to become 1 here too, correct? And 1 and 1 in an AND gate, it will be a 1 here, 1 and 1, it will be a 1 here. Yeah? So if both are 1, this is going to turn out to be 1. So now we came out with the entire truth table for this circuit, right? But we know that this configuration here is forbidden. Why? Because from an engineering standpoint, why would you put in a flip-flop to 1s? Yeah? and 2 zeros is supposed to preserve the previous state. Okay. By the way, guys, sometimes 1 and 1 preserves, in some circuits, preserve the previous state, but not in this circuit. So let's see another circuit. Let's see this circuit from sheet 3. We're going to do this circuit here, this one. Okay. See, this is 2 NOR gates. Here you go. So again, this is a flip-flop, and in a flip-flop where you have 2 NOR gates like this, right? If you put S right here and you put R right here, mark my words, the output is supposed to be here, and this is the complement. I'm gonna tell you what that is, what that means. So usually the output is across from sit, right? If you put sit here, the output should be here in this circuit, in 2 NOR gates circuit. Or if you put the S here, it's up to you. If you want to put the S here, expect the output to be right here. Okay? Okay. So to do the truth table for this one, we're going to put S. We're going to put S, R, Q bar, and Q. By the way, Q is supposed to be the output, and this is the complement, meaning in this circuit, this is always the opposite of this. Yeah? Okay, so let's start. So before we start, again, we're going to put all the possible configurations, 0, 0, 0, 1, 1, 0, 1, 1. This is how we do it. But again, we will start from this point. Why? Because we know this is a flip-flop, right? There's a feedback here. We know this is a flip-flop, and it's just going to make our life easier if we start from this, because now that we start 1 in S, we know that this Q here should be 1, and this one here should be 0. That's something that we know. Okay, so this is 1. Now, before we start, very quickly, oh, I'm not going to be able to erase this. Before we start, very quickly, you know that a NOR gate only outputs 1 when both inputs are 0, right? This gate only outputs 1 when both inputs are 0, right? Okay, so if we have 1 here, right? This one, because this is 0, since there's 1 here, so it's going to come out to be 0 here, correct? Why? Because this only outputs 1 when both are 0. Since one of them is not, which is this, so it will output 0. This 0 is going to go like this and ends up here. Okay, what's the value for R? It's 0. Okay, so now we have both inputs as zeros, so this is going to output a 1 right here, right? Because both inputs are 0, so it will be 1. 1 and 1 in a NOR gate, that becomes 0, and 0 and 0 in a NOR gate, it becomes 1. There you go. So 0 and 1, and that's what we expected. Okay, second cycle, we're going to do this. Why? Because we expect this to preserve the previous state, which is this. This is how the SR latch works. So we're going to put 0 in here. Since the second time we do this, or second cycle, we denote this by 2. 0 and 1, this will output 0, correct? Why? Because it needs both inputs to be 0 to output 1. Otherwise, it will output 0, which is this case. So 0 in here, right? Now we're going to input 0 in here, because we said both zeros. 0 and 0, this is going to output another 1. 1 here, right? Second time. So 0 and 1, this is going to output a 0. And here we have 2 zeros. In the second cycle, it will continue to output 1. So 0 and 0 will preserve the previous state, which is 0 and 1. Okie doke. What to do next? Let's change. We are going to change the input of R to 1. So 3. We're doing this now. Now, because we know that this is an SR latch or a flip-flop, knowing that putting 1 here should reverse this. This Q here, it should be 0. Let's do that. So 1 here, 1 and 0 is supposed to output 0. And here, right? 1 and 0, nor 0. And the input of S this time, look, it's 0 already. So 0. 0 and 0 in the NOR gate, that gives you 1. Oh, that gives you 1. And this one is going to end up here. Look, 1, it will end up here. So 1 here. So 1 and 1 in the NOR gate gives you 0. And 0 and 0 in the NOR gate gives you 1. So, as we expected, Q bar equals 1 now, and Q, which is the output for the entire flip-flop, equals 0. Now you see how R did reset the output to 0, and Q bar here is always the complement, which is the opposite. Guys, in circuits, once you see this symbol here, like if A equals 0, then A bar should be 1, right? That's why we are calling this Q bar and Q. So again, we know that this preserves the previous state. This keeps previous state. And we know that this is forbidden, right? Because again, in a flip-flop, why would you do this? But anyhow, we're going to do it to come up with the entire truth table. So we're going to put 1 in both cases just to check out what's going to happen. So we're going to put 1 here, and this is going to be a 4. 1 and 1 in a NOR gate, that gives us 0. Correct? And we will put 1 here too. So 1 and 0 gives us 0. So it's going to be 0 here. So 0 and 1 in a NOR gate gives 0. And 0 and 1 in the 4th cycle or 4th time. 0 and 1 again gives us 0. So here in the 4th time, if you set both to 1, you're going to get 0 and 0 in this cycle. Thank you guys for watching. I hope you benefited from this part of the tutorial, and I'll see you in the second part of this circles tutorial.